I would like to start and to tell you that my presentation is about optimization of concurrent storage and retrieval operations for real-time surveillance application. The word concurrent is important, and it means that we have one piece of the hardware and both types of operations performed on that piece of the hardware. So it is not like two independent servers. One does archiving, another does retrieval. It is the same thing, and they influence each other. That's the reason why there is optimization here, and how to do that. That essentially I'm going to talk about. Also, surveillance application. One of the important features of the surveillance application is backtracking operation. Backtracking operation means that you are able to find out the past behavior of the target. And in order to do that, you have to acquire all track of the target. I will show the picture. Yeah, there are targets here you see, like vessels, like airplanes, and you acquire their tracks and store it in the database. And if you want to know the past behavior of the target, you figure out the ID of the target and retrieve all tracks related to that ID. And essentially, you can build it here at the start, and you see, for example, definitely it was airplane, and you see the essentially trajectory of the plane. That's what you can do. Again, this work requires this type of operations. I mean, computer operations require significant amount of work, and that has to be done in real time. In real time, because you want to make a decision in real time. You don't want to see airplane flying and think what to do about it next day. So you really have to do that in real time, and real time means quite restrictive constraints. For example, could be less than 1 second, or maybe a couple of seconds. And during the many hours of data accumulation, you can accumulate quite a lot of tracks. So to retrieve that stuff quickly is not easy. And that's what I'm going to talk about. So here, essentially, our data sources, and you see different sensors. Some of them are airborne sensors, and they acquire data about vessels, and some of them vessels themselves, and they send their coordinates, and we record them. Some of them are just ground coastal radars, for example, and they acquire data about airplanes or other flying objects. And all of those data are published and subscribed by the archiver, and at the cumulative rate is about 500 messages per second. So you have about each message somehow about 3K. So you have about 1.5 megabytes per second, which is a kind of sizable records and sizable amount of data per server. A lot of time when I hear, oh, we have 50 megabytes per second, 100 megabytes per second, and you ask those people, oh, we have 10 servers, we have 20 servers. It's a big difference. So this is the data rate, and again, incoming data have to be stored in real time. You cannot accumulate data and create a bottleneck. Here is the design of the system. So you see ground sensors, maritime sensors, airborne sensors. All of them produce their data, convert them into XML format in order to allow relatively format-independent reading and receiving of the data. And that data go to the publish, subscribe, open, fire XMPP server, which you can subscribe, and archiver, for example, subscribes that data and store that data in real time in the MySQL database. It is essentially, you see it as essentially 3-tier architecture. So you have a presentation tier, you know, airborne sensors, that input type of things. You have a logical tier, which is web application server, and you have a database tier, which is archiver. Relatively familiar architecture with only one twist. We know very well that it is not good for real-time system, that type of architecture. So what we have to do, means that we have to select the parameters of our components, hardware and software, in such a way that provide real-time capabilities, even the architecture is not real-time. That kind of trick. So here you see the different kind of layers. And now we're talking about hardware selection, trying to compensate for the hardware, the drawbacks of the architecture, which is kind of given to us. And with the hardware, we had two candidates. Of course, we wanted to use common off-the-shelf, you know, stuff, the cheapest one, which is quite powerful. And the project was actually, that selection happened about 2 years ago, a little bit less. So at that time, we had multi-core Opteron and Xeon. On this picture, all of them have 4 cores, very similar, but internal architecture is different. You see here with Opteron, the data out of the core go directly to memory due to the memory controller implemented directly on the CPU chip. While on the Xeon, they go through the front side bus, and that essentially is a problem, because the more cores you have, the less time each core receives for the passing and receiving the data. And this is essentially a bottleneck. So we have to take into account and also do some benchmarking of that architecture. And that's what we essentially did. So we wrote the benchmark, and as a kind of testing thing for benchmark, we use conversion between XML and Java object. This is a very kind of resource-consuming operation. You have to go through the XML tree and convert it into Java. It's quite a lot of work. We use JAX-B conversion using JDK 1.6. And what we found interesting, that if you do many conversions, the speed of conversions changes, and the how to say it, the effectiveness of each architecture is changing as well. That is interesting. What I will explain what you see on the graph. Here's the line, and this is a line 0 or 1. Below that line, Xeon is more effective. The time for the conversion on Xeon is smaller. So Xeon is faster. Above that line, Opteron is fast. And here you see the number of conversions. So once you start with, and this is a logarithmic scale because a lot of conversions. So if you have like 10 conversions and you have marshalling and unmarshalling, depends on, you convert from XML to Java object or vice versa, it's marshalling and unmarshalling. And Opteron is much slower. Here you see how Xeon is much more effective. But once the number of iterations increases, means JVM getting warmer and warmer, the situation is changing, and probably the number of iterations required to convert is changing. JDK optimizes on fly. We use that advantage further as well, and the situation changes because we know there are going to be a lot of conversions. So after about 10,000 conversions, or even more, like 50,000 conversions, Opterons are better. And what's also interesting, that our conclusion corresponded to what Anand Tech, you know, that website which evaluates hardware. Yeah, they also ran some benchmark on similar what we have. We had 65 nanometer Barcelona versus 2.5 gigahertz. Versus Intel 3.0, 45 nanometer Xeon, which is much more efficient architecture, yes, significantly better. And it is interesting that Opteron hold out. Yeah, that's what, hold on. Yeah, and you see this, what Anand Tech did, they ran MySQL, and measured the queries per second. I don't remember what queries were, probably insertion, something like that. And they found that 2.5 gigahertz Opteron is more effective, faster than a dual core Xeon.
And that's all because of the controller and the memory and going directly in memory and.
I think it is a significant part of that. The latencies also, because of that, and the latencies on Opterons are significantly smaller. Significantly means could be like 4 or 5 times, and that not only, and actually the bandwidth or throughput. It is difficult. If I talk about those particular guys, the throughput, I think Opteron Barcelona has about 25 gigabytes per second, and Xeon has about 6.4. That's different. But what's also interesting, that time is changing. And recently, a few months ago, Intel released i7 architecture, which has exactly the same architecture as Opteron does. Yes, and I didn't work with that architecture, but I was told that it is blazingly speedy.
Part of the problem is arbitration, which core gets to use the I.O. bus, and that ended up using a lot more time than Intel expected in the real world. So when one core started cranking along, it was okay, but then when another core said, can I have a bit of that? And the first core said, no, I'm still busy. And then
well, that should be perfect for MySQL.
It depends. If you have multiple clients, you still have to switch.
Yeah.
So that, and we essentially bought, the Opteron-based system delivered by I/O with comparable CPU power. So now we can go to the database service selection, and first we look at the single client performance and multiple client performance after that. And the candidates were our lovely ones, MySQL and Postgres. In the group where I work, most of the people are big fan of Postgres. So it was not easy for me to bring MySQL in. And that was a significant matter. And I knew that MySQL, as with my sum, definitely better than Postgres with the transactions. I knew that. But you can argue forever, forward and back. So what I did, I wrote benchmark. And I wrote them, and I reasonably optimized Postgres and MySQL, and I found that for the one client, MySQL is about 3 times faster. Significantly faster, probably because of transactionality. Moreover, I found another strange thing. For the short records, it is kind of shaky. Look how nice MySQL behaves. Just straight line, goes ahead. And these guys, maybe the kind of vacuuming, I don't know what they're doing, because it's only an insertion. Nevertheless, so once I did benchmark, and also did it with multiple client performance, where MySQL also became faster, not as 3 times, but still faster. It is interesting that it was faster in spite of table locking.
Are you using MySum or?
MySum, right?
Yeah.
MySum. Even in spite of table locking, because I believe that table locking happened mostly in memory. Shiri, is it true?
I guess if your buffer is large enough, right?
Yes,
because
definitely large.
You can't really lock a table. You lock a file, right, on the file system. So yeah, I guess the table locking is mostly memory. So if your memory and your overhead and your context switching is a lot faster than
right.
I can
That's
see
what.
how that.
This is on a Linux system? Or
Yes. Oh yeah.
So there is also the cache for the Linux does some caching for the file system.
But it's the same caching on both MySQL and Postgres,
Right.
you would think. So the
Depends on the scheduler. There is a scheduler, and it depends how it works with it.
So now we're talking about schema design, and for schema we also had 2 designs. One of the design, and that's important thing again. It was a lot of arguing about that, because people wanted to store in the database raw data. It always makes sense to store raw data, no question about it. So people wanted to store raw data, and what it means is that, we converted XML message into Java object because we still need numerical fields to do searching. So you have to do that anyway. You cannot search inside XML. Forget about that. And the real speed, yeah.
Not in MySQL. Not in MySQL. I mean, text-based search. I don't know if Postgres is any better with text-based search.
I think not better.
Right.
Yeah,
Not anywhere close.
Right.
yeah, right. So, and after that, you inserted those numerical values into numerical table. That's simple. And after that, you insert the whole string into the XML table. That way you're going to restore it. And that's what we're going to do when you restore it. You go to numerical and got your essentially ID, something, and after that you go to the XML message and retrieve it back. So another design, and there are advantages and disadvantages. Advantages is that we're bypassing the marshalling of objects into XML. When we retrieve it, we store original data, which is nice, and we have a direct retrieval of original XML messages. But there are disadvantages. More complex schema. Now you have to do transactions to make sure that everything is in sync. And yeah, you have to manage 2 tables instead of 1. If you have a lot of them, it's kind of a problem. So we had an alternative proposal. Let's forget about original messages. If you have correct XML data, that's fine. Even in numerical format or in string format, the same thing. There is no difference. If you have a bad one, why you need to keep it? You're not going to do too much about it. So let's do the following. First, convert it into Java object and insert into numerical table. But when we retrieve it numerical numbers, and create from scratch original XML message out of that. And that's why we did. So there are advantages here by passing the storage of long XML messages, and the difference in size was 10 times.
10 times smaller.
Numerical was 10 times smaller, or XML was 10 times bigger. Yeah. Yes. Not by many reasons. You have a lot of tags, XML tags. You have inefficient ASCII. You have non-compressed things. Numericals packed pretty well. So there is a sense. But disadvantages that requires marshalling the object into XML string. And now, Sherry, exactly your question. What is faster, disks or CPU? Depends on what you're doing with them. Yeah, and for us, that was the test, when we knew what we were doing. So, can we unmarshal Java object into XML string quickly enough? And that's what we started to measure. And we did our familiar JXB conversion, and how many conversions per second we can do. And that's where the JDK 1.6 started to play really well. The dynamic nature of Java language, which allows you to reload exactly the same class, again, already optimized. It watches how it performs, sees the bottlenecks, changes the object file, and reload it. And it is better.
Is that the warming up you were talking about before?
Sort of, yes. Yes. But also there is memory distribution, so it might take more memory now. Yeah, allocate some things better.
And it's Java, it probably will take more memory, because that's what Java does.
It takes all
It takes all
It takes most memory, given enough time to...
What's good about it that you have now 64-bit. But look, now when you have like 10 conversions, each conversion takes seconds, up to like 6 seconds in the worst case, maybe even 7 till 2. But once you do 10,000, the conversion time drops, and after 100,000 conversions, it's essentially almost one millisecond. So if you see, after 100,000 conversions, JXB conversion time drops almost 1,000 times. Just software optimization. And that would essentially change the equation.
The JVM self-tuning.
Right.
Nothing that you guys...
No. You have to do that. You have to use parameters for the garbage collection, all of that stuff. Not a lot, but essentially 1.6 is quite well optimized. But we did a little bit of that. And here we measured the conversion because we had also some concern. Okay, it converts pretty well short messages. What about long ones? When you have a lot of tracks inside one message. And we did it up to 10,000 tracks. So if each track is about 1K, for example, so we have 10,000, it's about, yeah, few megabytes, good few megabytes. And yes, it loses its speed in some way, you see that, but still for 10,000 tracks, the time is less than 1 second. If you put so many tracks in, you're not going to have so many records to insert. Definitely, you just did it in one, like, you know, multiple insertion at once. Yes, and that's what we did, and here we analyzed the garbage collection because it was a concern that Java might have a leak. And now, after so many conversions, memory getting larger and larger, and we actually ran it for a few hours, and that's the garbage collection memory statistics, and it's almost, you see, it's almost linear. Yeah, and that before and after garbage collection. So that's what it is, and it is really, really good.
So why did the times go up so dramatically towards the end of the scale? I mean, you know, on the left-hand scale there and the right-hand side.
You're talking about this graph or about this one?
The graph on the left.
This one.
Yes.
Here, number of because it is when you have a long many number of messages, it's a lot of work.
It's a little misleading. The scale is logarithmic.
Yes.
So the curve is logarithmic. So it's actually a linear curve. But the numbers at the bottom are logarithmic. So it, you know, because
yes, so that's true.
So it's actually linear almost. It looks like it.
Can you explain one term to me? I'm sorry, I never heard the term marshalling. What does that mean?
You know what XML is about.
Yeah.
Yeah, you have a kind of tree of these things.
Yes.
But when you are writing the software you want to do, working with Java, for example, you really cannot work with that. You need to extract data out of that. And it's difficult. What's better to convert that XML into Java object. Typical our object which contains data. Actually, there is a one-to-one mapping between XML, you can create it, Java object, and relational tables. You know, like you can map objects to tables. We know that, ORM. Yeah, that's and there is a similar type of mapping between XML. That's what marshalling means, converting from converting from objects to XML, and then marshalling, converting from XML to object. When we are working in real time, getting data out of sensors, you cannot get all data in advance. You get them in a small portion. It's essentially a data stream. The whole presentation, in some way, is a kind of struggling with data streaming nature of data and trying to keep up with this type of things. So you got a small portion, convert it, store it somehow, and you maybe have to retrieve it as well. So going further, now we are able to store our stuff, and we have to recall what we are essentially trying to achieve. And what we're trying to achieve is fast retrieval of the data which we're looking for. And here in this section I will describe the backtracking operation and the search data flow and how we did indexation, because we cannot do that without indexes, of course, and composite indexes which we did. I even will describe a little bit what indexes are about, so it will not be very complex. And here you see our final task. So what we try to understand in real time is who potentially could launch the target. How to find out, like, the vessel which was the launcher for the target. And in order to do that, we know the target ID. We can track target back up to the surface, sea surface level. And once we go to that location, we can figure out who was nearby at that time and get a list of potential candidates. And now we can. So And after that, kind of deal with them one by one. Who is likely, who is less likely. So you see that this is a kind of volume of data for analysis. So we have two types of requests. One is the first request type when we're looking for object for ID and trying to find the backtracking things. And the second is the kind of geolocation things. So we know the location. Let's find all the guys nearby. And that two type of search, all of them, especially the second one, requires to search by many parameters. And that's a pain, essentially. Yeah, it's difficult. So here you see the data flow, and for the whole system, now we see the old one, which we used for acquiring the data, to store the data. You see that. The sensors and the archiver, but here, yeah, that's familiar 3-tier architecture, but now we see the second part, retrieval part, which starts from the user, who sends HTTP request to the web server, and web server gets that request, parses it, and runs the servlet, which in turn converts request into the query, and runs that query in the database, and returns some results, retrieves the results. After that, it converts records to XML string, you know, our lingua franca, parses XML string for the client, because client needs to get the data out of it. And finally, client can display the tracks, which I showed at the beginning, and see what the trajectory was. Yeah. That is the overall architecture of the system. Essentially two parts. One part which is pumping data in, and another part which is pumping data out. Relatively quickly, but not as fast as we can, at least, which is good. Here we understand that in order to retrieve the data quickly, we need to use indexes. Also, we need to reduce the dependency between size of accumulated data and the time which we need to retrieve the record, to find the record among them. Of course, to find the record in 10,000 records, it is different than to find one record among million records. But for our user, they don't care about that. It's our problem to do that. So we definitely have to use indexes. And here I'm explaining what indexes are about. But the problem with indexes, that in the usual way how people use indexes, they acquired all the data, created the table, finished data acquisition, and after that apply indexes to the whole table. Indexes work. They kind of sort out the data, and after that they retrieve necessary records using already ordered indexes. So that's kind of known thing. In our case, we cannot do that because ordering indexes for the whole table takes a lot of time. It's prohibitive. We cannot do that. So what we should do? How to solve that? And without indexes, we also cannot work. So this is a traditional approach. Store data in the table, add indexes to the table once the data accumulation finished, and retrieve data. Here we use different real-time approach. The problem is that first time you acquired your data, apply your indexes, your table is essentially empty. There are very few records, and you can sort indexes very easily because there are very few of them. The next step, you acquired one record. You added one record to the previously existed records. And now you have to sort it out. It's not a big deal, you know, one record more. Sorting will take very small time. Now you add another record to already sorted records. It's not a big deal. It is really like, you know, people ask, what does it mean, big pile? 3 items is a big pile. Not really 4. Oh, yeah. So that it is interesting that that type of indexing does not take too much time, and we could get away with that very successfully. But still, indexing influence the insertion speed. They do, but not as significant as in traditional approach, but still does. And that what for us was a problem, because if it influenced insertion speed significantly, we don't want that. We cannot use it. So for us, it was a matter of essentially, can we do that or not?
Now, when you're talking about the traditional batch approach to indexing, you're talking about like OLAP stuff, right?
Yes.
You're talking about doing the ETL and
Right,
transformation,
right.
because I'm looking at this and I'm like, but that's what indexes are. They're continuous, because when you're dealing with an OLTP system, you're dealing with that. So you really do kind of have the worst of both worlds of OLTP and OLAP. Where you
Exactly. Yes, Sherry, you're right. Yeah. I call it real-time data warehousing. And people kind of, a couple of times I used the term talking to people. Some of them got angry. What do you mean? It cannot be. There is no such thing. It's oxymoron. In our case, unfortunately, we had additional complications because we had not one index to use. We had multiple parameters to search. And now you have, so leftmost rules. So we wanted to have a composite index. Composite index allows you to search for multiple indexes very efficiently, like essentially jumping over on the head of each index sorting. But your indexes have to satisfy some conditions. I don't know how to explain it very quickly because I read it multiple times, kind of not easy to understand it in a second. So indexes have to satisfy some conditions to create efficient composite index. If they don't, now you have to create another index. Completely separate one means that database will do more work, the hardware is going to do more work, and in our case, unfortunately, that was the situation. We had to index many columns, and almost all of those indexations was independent. Means quite how much real-time index updates, slow real-time insertion. And that's what we did, and now we're coming to the final part, measurement of the influence of the indexing operation on the insertion operation. Essentially, this is a synthesis. What is your break-even point?
The difference between a composite index and multiple independent indexes on the same table. So the reason why you couldn't use a composite index is because the items being indexed were mutually exclusive.
They require indexing columns which were not leftmost.
What you're doing is you have 4 indexes, but what you want to do is when you retrieve on the first index, you retrieve as few records as possible.
Right.
That you want to discard as many so that you're passing on to the next filter. You're running it through a series of filters. And so you pass through as few.
Right, so your filters are connected subsequently, one chain. If your index is not allowed to create that smooth chain, you have to create another chain to do that. Not necessarily, depends on which columns you indexing. If you don't index them in a row, column 1, column 2, column 3 or something, you cannot reduce the amount of calculation. You have to create separate independent index for that. That's leftmost.
It's like if you were trying to retrieve SQL programmers and you want to get my record, you would not want to look for SQL programmers within this meetup group. You'd look for people that were in Reddit, because there's very few of those, and then check how many, there might be 1, 2, or 3 maybe that return from that, and look for those to see which ones are.
Name starting with L, for
Yeah.
instance. So basically, you could use a composite index, but it would return a lot more value than doing, index on column A and then an index on column B.
We have devices that are hooked up to cell networks and they move around, and we want to be able not only tell how many devices over a time period were in a certain geofenced area, but then there are other times we want to know where did this device go. Sometimes we're tracking it by the actual router ID and where it physically goes, and other times we don't care about which router it is. We just want to start off with latitude and longitude and a date. And then we'll find everything that's inside that. Those are 2 completely different lists of numbers and 2 completely different sets of indexes. But there's that's where this kind of comes in, where sometimes they're looking for two different answers entirely.
So that is indexing, and now we are trying to measure the effect really numerically. We have a break-even point where we have to stop to add indexes because it slows down the insertion so significantly that we cannot do that. The design is the design of the benchmark. So the archiver pumps in the data constantly, and the searches in that data also constantly, like a loop. Here you increase the number of indexes, and you will see how they balance. Because searching will be faster, but storing will be slower. It kind of makes sense, but the problem with that approach are the data. Because you cannot really, if you want to measure something, natural data are not good, because you don't know what you're going to get back. You don't know how many records you're going to find in the natural data, so you cannot compare to situations. Oh, that happened because you found 1,000 records. Oh, that happened quickly because it found only one. You really need to have simulated data. But with the simulated data, you have another problem. They should be similar like a natural one, but have the properties which allow you to do measurement. And that was a difficult thing to do. And the idea was, if I'm searching for a particular record, if accidentally that record was the first in the table, I found it very quickly. If the record was the last one in the table, it's also unfair. So I really would like to have kind of uniform distribution in some way. Also, I would like to know how much data I'm going to get in advance, because it influences the search time. So how to generate that data? And the idea was to use waves. What it means, for example, I'm searching for records with particular altitude. And I created those kind of waves in such a way, through the whole my table, whole my records, there are 10 summits with this particular altitude. And I know if I search for the values little bit less than that, I'm going to find 10 records. I know that. Searching for the whole table. And I can distribute them relatively evenly along the whole table. If I reduce my criteria a little bit more, I'm going to find, as you see here, more records.
Jacob, are you saying that your data is distributed as a function of, for example, altitude, that the lower the altitude, the more data that you have?
Yes. That's how I generated for the altitude, but I also did the same thing for the latitude and the longitude. So here, changing the threshold, I can manage how many records I'm going to find in advance. And now I can measure, now I can compare.
So when you want to test how long does it take to get 1,000
exactly,
records, you can do that. How long does it take to get 100 records?
Exactly.
Exactly.
That's
as opposed to randomly testing latitude and longitude and hoping that you didn't just, end up on, this port, Oakland, California or something.
Right. And that was important for measurability things. And record time is a record number multiplied by delta. The only thing which was not wave-like was the time. Because time is linear, and I just change the boundary, I can figure out how many records, particularly in the time, I can do.
Assuming your simulation
Right.
put things in
Yes.
Because in reality, different things move at different rates.
Yeah. It worked very well for latitude and longitude, because for database doesn't care is it latitude or longitude, it's just numbers. But what's important, the combination of that. Now I have 2 indexes, 3 indexes, 2 numbers to search for, more and more, and it really loads server differently.
Did you do any proximity searching? You didn't use geodata, right, or spatial types or anything, you just used regular numbers?
Yeah, essentially doing the squares. Here I measured non-index search. How speedy the search is when we don't use indexes. And it is not easy to see because it's a small scale. I will explain to you. What you have here is a number of records in the table. Here it's about 100,000, and here it's a 10.7, means 10 millions. And here is a search time, how much time the search required. And here is 1 record, 10 records, 100, and 1,000 records. So what is interesting here, look, it is almost linear up to more than 1 million. And by the way, the different color is a different architecture. The red one is a 32-bit architecture. And those guys are 64-bit architecture.
Wow.
It is interesting. All of that stuff is Linux, no Windows. So what it means is that the size of the memory, of course, much smaller for 32-bit. You cannot have more than 4. And for those guys, I have 16 for 64-bit. Of course, you can say it's unfair comparison. I agree with you. But unfair comparison, I don't care. You see, I have architectures and I would like to compare them, fair or not, to see what I can get out of them. And it is interesting that after so many records, it just jumps, because something doesn't fit into memory. That's what I believe. And you have, this is 64-bit is much linear, because this is more memory. But it's still, you see the significant non-linearity, or increase, I would say. And now look, comparing with the index search. That's interesting. It was not only straight line, but how, look, if you look at those numbers here, you see 20 seconds, you see 10 seconds, 15. Here you have, wow, you have 30. What you have here, fraction of a second. And even in the worst case, 1,000 records, you still have 0.3. Up to 10 power 7. So 10 million records. But I did measure that for 100 million records. And it was linear. Now we know that we need index search, but what about insertion time? And now we started to measure that. That's where the break-even point is. And it does slow down. If you look, for example, originally we had 7,000 records per second insertion, when we had 2 columns only indexed. But when we indexed almost 20 columns, the insertion speed was about 5,000 records, only 30% reduction, significant. We can now compare it with required insertion rate. And we see that required insertion rate was only 500. So, yes, from insertion point of view, we are fine with indexes or without indexes. But from retrieval, not at all. You cannot retrieve as it is necessary. This is the required retrieval time, and without indexes, it is above that, and with indexes, we're under that. So, we did it.
Can you go back to the previous slide for a minute?
Uh-huh.
How do you explain that red line at the end? It seems to be a little different. In the index,
Uh-huh.
the red one, how
Yeah.
do you explain the cause of that pattern for the red line?
You talking about?
Why is it so crazy? Why does it go up and down?
Why is there a hump in the middle?
Why is it up and down?
I don't know, frankly. You see, it is a significant difference in number of records. It's 100,000 records and 10 million. Why not? I know that in my previous presentations I found MySQL has strange things. But here it's a 5.1. 5.124 probably. I did 4.1 and 5.0, and for particular record length, they have something. And it is very consistent. I talked to Monty about that. Monty didn't know about it. Yeah, completely. He was very surprised, and actually it happened even with kind of strange story, because I told him that 4.1 has a better insertion speed than 5.0. My son, yes. He didn't like it, but he said, Jacob, I would like to verify what you have done. Of course, and I sent him all Java files, all data.
I can't read the indexes. Is that all within, like, between that up and down red line and the blue line, is that really, like, only, like, 50 milliseconds?
Right. It is not a big difference here. And between architectures, because 32-bit actually quite fast. The only problem with them, when you have not enough memory. And by nature of 32-bit, you do not have enough. Yeah. So we're essentially done. We verified that we can do that. We got required search time. Indexes, yes, it required a lot of benchmarking. It was risky. Because when we started that project, we didn't know that we will be able to do that. The previous project, which did similar thing, actually failed. Failed miserably because of the JAX-B conversion time. They use JDK 1.5.
But what if you bypass all these layers and insert directly, putting in a...
Oh, you mean there is a way to do that? There is a way to do that just taking data out of XML. There's the XPath, or you can do even the splitting things.
For me, it's a lot of overhead to put in XML, then put in...
You're absolutely right.
And
Yes.
then going to the database. When you
I am always telling them XML is a wrong way of passing a lot of data. It's a wrong way. In addition to huge overhead, there is a major drawback that it couples the data. If you don't need the whole XML stuff, you have to have it. Do you want it or not?
Right.
And
So
then
you even need one
Yeah,
number.
if you need one number, you stuck. I would prefer sensors to send data in the database directly, because it is better in many aspects. Because it's proprietary protocol, it's much more efficient than stupid ASCII protocol which they use, and nobody cares what transport protocol you use. Who cares what's inside, what between endpoints? You only get data either here or there. You don't care what electrical signals between there. You're not going to read them.
How much smaller than 1.5 megabytes per second would your data be if it wasn't in XML format?
Oh,
That's the XML
significantly.
format,
I tell you, I calculated in a level of inefficiency of our system. Unfortunately, it was not only XML. We had some other inefficiencies, and it was about 1/10 of the percent.
Wow.
Wow.
Is the
1/10 of the percent is efficiency.
1,000
means-
times less efficient
Right,
using
right.
XML.
But is that data stream being used for other things besides your use? Because that would-
Yes, yes, but it still could be used through the database, because I believe that publish-subscribe is not a good paradigm for data delivery. Publish-subscribe was originally created for sending alarm signals. XML is a bad transport for dealing with the streaming data. Really bad thing. But you can get away, if you put huge server, modern Java or whatever, yeah, you can get away with it.
To me, it would make more sense if I could choose, it would be to have the data streamed in the most efficient manner possible, and then at the point where you have, there's points where you have to have XML for commonality, but at that point you put an interface and then you just map you have proprietary drivers that more or less that map the incoming proprietary stream to an XML data structure and then ship that off, but only when you need it.
Convert it farther down the line.
Much farther down.
Yeah, so here is a summary, and we benchmark hardware, demonstrated that Opterons are good. I heard that Opteron is still good even in spite of improvements of what Intel did. They now also work with a 45 nanometer architecture, the latest Shanghai server, 45 nanometers, quite fast, quite reliable. People like it quite a bit. Controller influence that stuff significantly. So you might have a wonderful Intel machine, but with a not good controller. Here we also investigated search with a constant flow of insert queries and demonstrated that without index we really cannot do that. That was difficulty to work with streaming data. So we also measured the break-even point and found that it is still better than what our requirements are. That's essentially it.
Well, thank you, Jacob. Thank you, Jacob.
What about deletes? Do you ever need to delete data?
No, I'm lucky because I'm working with experimental data. You never delete them. You never update experimental data. That makes too much
But
sense.
at some point, doesn't it just get so huge? Like, what happens, you do 1.5 megabytes per second. What happens after, like, a month?
After like a month,
use all
you
your storage.
offload it and store it for people who will analyze it later.
But it's MySQL, so you can just copy it.
Yeah, that's kind of course, with that is why I got away with my sum tables, because you don't need transactions, because there is no actually conditions when you need essentially transactionality.
Right.
One last question. Is your test like available? Are they scripts or something that you make available? Are they proprietary?
No, there is nothing proprietary over there, but I use combination of Java and shell scripting. My low operations are in Java, but when you do repetitions and all of that stuff, that's in scripting. I just called many times.
So you're running the Java on the same machine as MySQL. I wonder if that maybe would contribute to some of the wonkiness in the 32-bit memory.
Yes.
Because the only thing worse than somebody running MySQL on a 32-bit platform is running, Tomcat SQL.
Yes, I run it on the same machine, but I believe if you allocate particular amount of memory for the MySQL in CNF, it takes it.
Yeah, but there's still the overhead and the context switching and stuff. So if it's, it will take it, but if it needs more or whatever, and if Java's doing the garbage collecting, maybe part of that craziness that you're seeing is partially Java kind of, doing its optimization so that it, the peak in the middle might have been where Java
I see what
was really
you're saying.
optimized with the
Over
thing, and
there.
it's freeing more memory that MySQL could then take. I don't know. I'm just making stuff up here because if you, but if you are doing that, then there may very well be the limit per process. Because the limit per process is theoretically 4 gigs, but in reality for MySQL, I haven't seen it much more than 2.456 or so. I don't think I've really seen it get up to 3 or 4 gigs of memory.
The problem...
Not a 32-bit because it's
No, 32-bit, no. But the problem is, I don't want to... I thought what you're saying about, but I'm also constrained. I don't want to introduce network into that deal.
Right.
Really, I don't want that.
It's
I
all
have nothing to do with
speculation.
that.
In some degrees, it doesn't
Now
matter
you don't know what you're dealing with.
Right.
And that is because my previous benchmarking, I did quite a bit of them. I did use networking, and it is a problem.
Because that's the biggest bottleneck.
With bottleneck, and you don't know even somebody started doing something over there.
And to some degree, it doesn't matter why the 32-bit was wonky, because the ones that you found it much better. So, to some degree, it may not even matter why.
In some way, I just did with 32-bit just to show.
Right.
Because forget about 32-bit.
Right.
Yeah, nobody, essentially none, uses it now.
Did you pass any switches to limit the amount of memory or to give a certain amount of memory to the Java client?
Yes, we did. We did. I don't remember the numbers. We did it when we estimated the garbage collection for the JXD conversions. Yes, we did it. It is a tricky thing to compare 32 and 64, and I used to do that some years ago. Even comparing 64 in MySQL with the 32, exactly the same as everything the same. On 64-bit platform, I put 32-bit MySQL, 64-bit MySQL. Difference in performance, 10%. I also forgot to tell you that with indexes, load on CPU is very low, amazingly low. I was surprised with those benchmarks. CPU is loaded 25%. 30, something like not more. Yeah, and I did even worse benchmarking a couple of years ago. I did as fast as I can, pump in, pump out, and I had about 20 clients pumping in and about 120 pumping out, reading. Opteron 8000, 10 RPMs. Disks for CPU, but each CPU at that time was only 1 core, 50% load. Yeah, it is a very efficient way of dealing with such